When sizing panel feeders, the National Electrical Code, or NEC, requires that the panel feeders be sized based on the actual calculated load, not the size of the panel itself. This ensures the feeders are adequate to safely handle the current the panel will draw. Consider an example where there is a 405 amp load and a 600 amp panel. In this instance, the feeders must be sized for 405 amps. Even though the panel is larger than the calculated load, the feeders must be sized to protect the conductors and equipment from overheating. There are several reasons for sizing feeders based on the calculated load. Firstly, safety is paramount. Oversized feeders could create a safety hazard by allowing excessive current to flow through the conductors, potentially causing overheating, fires, or other damage. Secondly, code compliance is essential. The NEC specifically prohibits sizing feeders based on the size of the panel. Refer to NEC Section 408.3b, NEC Section 408.54, and NEC Section 408.36d for more information. Thirdly, sizing feeders based on the actual load allows for future expansion or changes in the building's function without overloading the feeders. Fourthly, efficiency is a concern. Oversized feeders can be less efficient and waste energy due to the increased resistance of the conductors. However, the NEC does provide an exception that allows feeders to be sized based on the panel size when the panel is dedicated to a single motor. In this case, the feeders may be sized for the full amperage rating of the panel. In summary, the general rule is to size the feeders according to the calculated load to ensure safety, code compliance, future expansion capabilities, and efficiency. Only in the specific case of a panel dedicated to a single motor does the code permit sizing the feeders based on the panel size. The NEC provides specific guidance on panel board requirements, including those related to feeder sizing. Panel boards must have a rating not less than the minimum feeder capacity required for the load, calculated in accordance with Article 220. This means the panel board itself must be appropriately sized for the expected load. Overcurrent protection is a critical aspect of panel board design and feeder sizing. Panel boards must be protected by overcurrent protective devices that do not exceed the panel board's rating. This ensures that the panel board is not subjected to currents beyond its capacity, preventing damage and potential hazards. The overcurrent protection must be located at the point where the feeder conductors receive their supply. For example, if a panel board has a rating of 200 amps, the overcurrent protection, such as a circuit breaker or fuses, must not exceed 200 amps. This protection should be placed at the beginning of the feeder conductors. Panel boards used as service equipment require specific considerations. Service equipment refers to the main disconnect and overcurrent protection for the entire electrical service of a building. Panel boards used as service equipment must have a main overcurrent protected device. The rating of this device must not exceed the rating of the panel board. Additionally, the overcurrent protection must be suitable for interrupting the available fault current at the service equipment. Available fault current is the maximum current that can flow during a short circuit condition. The overcurrent protection must be able to safely interrupt this current to prevent equipment damage and ensure safety. The NEC also addresses the installation and use of snap switches in panel boards. Snap switches are commonly used for controlling lighting and other small loads. Snap switches used in panel boards must be rated for the voltage and current they will be subjected to. They must also be suitable for the type of wiring method used in the panel board. For example, if a panel board uses non-metallic sheathed cable, the snap switches must be listed for use with this type of cable. The NEC includes requirements for the physical arrangement of panel boards to ensure safety and ease of maintenance. Panel boards must be installed in a readily accessible location. This means that they should not be obstructed by equipment, storage, or other items that would prevent easy access. Sufficient working space must be provided around panel boards to allow for safe operation and maintenance. The working space must comply with the dimensions specified in NEC Section 110.26, which vary depending on the voltage and the presence of exposed live parts. Panel boards must be securely mounted to prevent movement or vibration. They must be installed in a manner that protects them from physical damage such as impact from equipment or machinery. The NEC also specifies requirements for the grounding of panel boards. Grounding is essential for providing a low impedance path for fault currents, which helps to protect equipment and personnel from electrical shock. Panel boards must be grounded to the building's grounding electrode system. The grounding electrode system typically consists of a grounding electrode, such as a ground rod or a metal water pipe, and a grounding conductor that connects the panel board to the electrode. The grounding conductor must be sized according to NEC section 250.122, which is based on the size of the unrounded conductors. Neutral conductors in panel boards must be properly sized and identified. The neutral conductor carries the unbalanced current from single-phase loads and serves as the reference point for voltage measurements. The neutral conductor must be sized to carry the maximum unbalanced load. In many cases, the neutral conductor is permitted to be smaller than the phase conductors, but it must be sized according to NEC section 220.61, which provides guidelines for calculating the neutral load. Neutral conductors must be identified by a white or grey color. This makes it easy to distinguish them from the phase conductors, which are typically black, red, or blue. Bonding is another important aspect of panel board wiring. Bonding refers to the electrical connection of metal parts to create a low impedance path for fault currents. Panel boards must be bonded to the equipment grounding conductor. This ensures that any fault current will quickly flow back to the source, tripping the overcurrent protective device and preventing a shock hazard. Bonding jumpers must be used to connect metal enclosures, raceways, and other metal parts to the equipment grounding conductor. These jumpers must be sized according to NEC section 250.102, which is based on the size of the circuit conductors. The NEC includes requirements for the identification of circuits in panel boards. Each circuit breaker or fuse must be clearly labeled to indicate the load it serves. This helps to prevent confusion and makes it easier to troubleshoot problems. The circuit directory must be updated whenever changes are made to the wiring. This ensures that the directory accurately reflects the current configuration of the panel board. The NEC also addresses the use of surge protective devices, or SPDs, in panel boards. SPD are used to protect sensitive electronic equipment from voltage surges caused by lightning, switching, or other disturbances. SPD must be installed in accordance with NEC section 285. They must be located as close as possible to the equipment they are protecting. The NEC also includes requirements for the use of arc fault circuit interrupters, or FSIs, in panel boards. FSIs are used to detect arc faults, which are a common cause of electrical fires. FSIs must be installed in accordance with NEC section 210.12, which specifies the locations where FSI protection is required. In addition to the general requirements for panel boards, the NEC also includes specific requirements for certain types of panel boards, such as those used in healthcare facilities or hazardous locations. These special requirements are designed to address the unique hazards present in these environments. Healthcare facilities, for example, require isolated power systems to protect patients from electrical shock. Hazardous locations require explosion-proof equipment to prevent ignition of flammable gases or vapors. Understanding the NEC requirements for panel boards is essential for ensuring the safety and reliability of electrical systems. By following these requirements, electricians and electrical engineers can help to prevent electrical fires, shocks, and other hazards. It is also important to stay up to date on the latest changes to the NEC, as the code is revised every 3 years to reflect advances in technology and changes in industry practices. Consider the specific requirements outlined in NEC section 408 regarding switchboards and panel boards. The NEC defines a switchboard as a large panel, typically floor-mounted, that contains switches, overcurrent protective devices, and other control equipment. A panel board, on the other hand, is a smaller enclosure, typically wall-mounted, that contains overcurrent protective devices and is used to distribute power to branch circuits. The NEC provides specific requirements for the construction of switchboards and panel boards to ensure their safety and reliability. Switchboards must be constructed with a metal enclosure that is grounded to the building's grounding electrode system. The enclosure must be designed to protect against physical damage and to prevent the accidental contact with live parts. Panel boards must also be constructed with a metal enclosure, but the enclosure may be surface-mounted or flush-mounted. The NEC also specifies requirements for the arrangement of devices within switchboards and panel boards. Devices must be arranged in a neat and workmanlike manner, and they must be securely fastened in place. Sufficient space must be provided around devices to allow for safe operation and maintenance. The NEC includes requirements for the overcurrent protection of switchboards and panel boards. Switchboards and panel boards must be protected by overcurrent protective devices that do not exceed their rating. The overcurrent protective devices must be located at the point where the feeder conductors receive their supply. The NEC also specifies requirements for the grounding of switchboards and panel boards. Switchboards and panel boards must be grounded to the building's grounding electrode system. The grounding conductor must be sized according to NEC section 250.122, which is based on the size of the unrounded conductors. The NEC also addresses the use of surge protective devices, or SPDs, in switchboards and panel boards. SPD are used to protect sensitive electronic equipment from voltage surges caused by lightning, switching, or other disturbances. SPD must be installed in accordance with NEC section 285. They must be located as close as possible to the equipment they are protecting. The NEC also includes requirements for the use of arc fault circuit interrupters, or ASIs, in panel boards. ASIs are used to detect arc faults, which are a common cause of electrical fires. ASIs must be installed in accordance with NEC section 210.12, which specifies the locations where ASI protection is required. In addition to the general requirements for switchboards and panel boards, the NEC also includes specific requirements for certain types of switchboards and panel boards, such as those used in healthcare facilities or hazardous locations. These special requirements are designed to address the unique hazards present in these environments. Healthcare facilities, for example, require isolated power systems to protect patients from electrical shock. Hazardous locations require explosion-proof equipment to prevent ignition of flammable gases or vapors. The NEC addresses the requirements for feeder taps. A feeder tap is a conductor that branches off from a feeder to supply power to a smaller load or a subpanel. Taps are permitted under specific conditions to simplify wiring and reduce costs, but they must be installed in accordance with NEC guidelines to ensure safety. There are several key considerations when working with feeder taps. Firstly, the tap conductor must be protected from overcurrent at its point of supply. This means that the tap conductor must be connected to a circuit breaker or fuse that is sized to protect the conductor from overcurrent. Secondly, the length of the tap conductor is limited by the NEC. The length of the tap conductor depends on the size of the tap conductor and the size of the feeder conductor. Thirdly, the tap conductor must be installed in a raceway or cable assembly that provides physical protection. This helps to protect the tap conductor from damage and to prevent accidental contact with live parts. The NEC recognizes several different types of feeder taps, each with its own specific requirements. The most common types of feeder taps include the 10-foot tap, the 25-foot tap, and the transformer tap. The 10-foot tap is the simplest type of feeder tap. It is permitted to be used when the tap conductor is no more than 10 feet long and is protected from overcurrent at its point of supply. The 25-foot tap is similar to the 10-foot tap, but it is permitted to be used when the tap conductor is no more than 25 feet long. The transformer tap is a special type of feeder tap that is used to supply power to a transformer. The transformer tap is permitted to be used when the tap conductor is connected to the primary side of a transformer and is protected from overcurrent at its point of supply. When installing feeder taps, it is important to follow all of the NEC guidelines carefully. Failure to follow these guidelines can result in a fire or electrical shock. It is also important to consult with a qualified electrician to ensure that the feeder taps are installed correctly. The NEC also addresses the requirements for voltage drop in electrical circuits. Voltage drop is the decrease in voltage that occurs as electricity flows through a conductor. Voltage drop can cause problems with electrical equipment, such as reduced performance, overheating, and premature failure. The NEC recommends that the voltage drop in feeder and branch circuits should not exceed 3%. This means that the voltage at the load should be at least 97% of the voltage at the source. To minimize voltage drop, it is important to use conductors that are large enough to carry the current without excessive voltage drop. The size of the conductor depends on the length of the circuit, the amount of current flowing through the circuit, and the type of conductor material. The NEC provides tables that can be used to determine the appropriate conductor size for different circuit conditions. It is also important to ensure that all connections are tight and clean. Loose or corroded connections can increase resistance and cause voltage drop. In addition to conductor size and connections, there are other factors that can affect voltage drop. These factors include the type of load, the power factor of the load, and the temperature of the conductor. Inductive loads, such as motors and transformers, can cause more voltage drop than resistive loads, such as lights and heaters. Loads with a low power factor can also cause more voltage drop. The temperature of the conductor can also affect voltage drop, as the resistance of the conductor increases with temperature. The NEC also addresses the requirements for short circuit current ratings, or SCCR, of electrical equipment. The SCCR is the maximum short circuit current that an electrical component or assembly can safely withstand without sustaining damage. It is important to select electrical equipment with an SCCR that is high enough to withstand the available short circuit current at the point of installation. The available short circuit current is the maximum current that can flow during a short circuit condition. The available short circuit current depends on the size of the utility transformer, the impedance of the conductors, and the presence of other current limiting devices. The NEC requires that all electrical equipment be marked with its SCCR. The SCCR must be clearly visible and easily accessible. It is also important to verify that the SCCR of the electrical equipment is adequate for the available short circuit current at the point of installation. If the SCCR of the electrical equipment is not high enough, it can be damaged or destroyed during a short circuit condition. This can result in a fire, electrical shock, or other hazards. There are several ways to increase the SCCR of electrical equipment. One way is to use current limiting devices, such as fuses or circuit breakers. Current limiting devices can reduce the amount of current that flows during a short circuit condition. Another way to increase the SCCR of electrical equipment is to use equipment with a higher SCCR rating. Equipment with a higher SCCR rating is designed to withstand higher short circuit currents without sustaining damage. The NEC also addresses the requirements for overcurrent protection of electrical circuits. Overcurrent protection is the use of fuses or circuit breakers to protect electrical circuits from overcurrents. Overcurrents can be caused by short circuits, ground faults, or overloads. Overcurrents can cause damage to electrical equipment, insulation, and wiring. They can also cause fires and electrical shocks. The NEC requires that all electrical circuits be protected by overcurrent protective devices. The overcurrent protective devices must be sized to protect the conductors from overcurrent. The size of the overcurrent protective device depends on the ampacity of the conductor. The ampacity of a conductor is the maximum current that the conductor can carry without overheating. The NEC provides tables that can be used to determine the ampacity of different types of conductors. Overcurrent protective devices must be located at the point where the conductors receive their supply. This means that the overcurrent protective device must be located at the beginning of the circuit. Overcurrent protective devices must be readily accessible. This means that the overcurrent protective device must be easily accessible and not obstructed by equipment or storage. The NEC also addresses the requirements for ground fault circuit interrupters, or GFCIs. GFCIs are used to protect people from electrical shock. GFCIs work by detecting ground faults. A ground fault is a condition in which current flows through an unintended path to ground. Ground faults can occur when insulation is damaged or when a person comes into contact with a live wire in ground. GFCIs are required in certain locations where there is a high risk of electrical shock. These locations include bathrooms, kitchens, garages, and outdoor areas. GFCIs must be installed in accordance with the NEC. The NEC specifies the locations where GFCIs are required and the types of GFCIs that must be used. GFCIs must be tested regularly to ensure that they are working properly. The NEC recommends that GFCIs be tested monthly. To test the GFCI, press the test button on the GFCI. This will trip the GFCI and cut off the power to the circuit. If the GFCI does not trip, it is not working properly and should be replaced.